Okay, can everybody hear me? Would you say yes? Okay, so thank you very much. Okay, so welcome back, and we're gonna finish. Today we're gonna finish the discussion on first order logic resolution. So here's a quick reminder about where we are. So we are considering this idea of first order resolution, first order logic resolution, because the the resolution theorem that we learned before was not quite, quite ready for algorithmic implementation. So if we want to design automatic theorem prover for first order logic, the previous theorem provided a foundation, but it was not enough. That's because the theorem say, in order to solve this, check the validity of a formula, we somehow should become a fortune teller and should figure out what kind of ground substitutions are necessary. And that should be done first. And then after that, we have to apply the propositional logic resolution proof system or resolution prover to derive a contradiction. But the first phase, there are infinitely many possible groundings of quantified formulas. So that's not quite ideal. So what kind of things that we want to have is, we want to combine these two steps together. Grounding, in other words, substituting variable by some specific terms, and at the same time, the process of deriving contradiction by resolution proof system. We want to put these two things together. So this first order logic resolution is designed to address this concern. So the resolution that I'm talking about is not, previously the propositional logic resolution is mostly about, in a sense, cancellation. But first order logic resolutions talk about not just cancellation, but about instantiation of variables. So if I give a reminder about this definition, okay, the pen. So we said, if we have a C1 and C2, they are clauses which do not have any variables in common, okay? And they are clauses from first order logic, so they can have a predicate, the atomic predicate applied to a bunch of terms, and these terms may have variables. And then we say R, which is another clause in first order logic. We said that's a reservant of C1 and C2. If it does the two things, first, it figures out what kind of substitution we have to apply. So that's what this first part is talking about. The second part is about what we usually know about resolution, which is about canceling. Okay. So you say that this R is a reservant of C1 and C2. If there is some subset of clauses in C1, so D1 is a set of literals. Another subset of clauses in C2, that's another set of literals, such a way that D1 and the complement of D2, so we put a negation to every literal in D2. So D1 union complement of D2 is unifiable. So that's what this first condition is saying. And then there is a because it's unifiable by the unification theorem, we know that there exists a most general unifier theta. And the second condition says, now if we apply this most general unifier theta to C1 and C2, and this everything in D1 will be collapsed if we apply this theta. So everything in D1 will become the singleton L. So this is really a singleton set L. Everything in D2 will become another singleton set negation of L, which is L bar. So what we do is that after applying the substitution, we remove these canceled literals from the C1 theta as well as C2 theta. So this is a usual step in resolution. Resolutions. And then this is something unique to first order part. Okay, so, and then one thing that I want you to notice is here we are not really applying arbitrary substitution at all. We are just applying substitution we are just substituting variable just enough so that we can derive this, we can obtain this L and L bar. In other words, we can do this cancellation. Also, when we apply the, think about the substitution, we always consider the most general unifier. So reservant of C1 and C2, in a sense, is the one where we applied as few substitution as possible, just enough to get the complementary literals in C1 and C2. Okay. So that's the definition of the reservant in first-order logic. And then in general, if C1 and C2 have some variables in common, we are considering the reservants for the renamed C1 and C2 by some renaming substitution theta 1, theta 2. Renaming just means it maps variables to some different variables while mapping different variables become different variables. So it just rename variables so that there are no overlap between C1 and C2 over the variables. Okay, so and then R is a reservant of this renamed C1 and renamed C2. So that's the definition of substitution, the reservant. And now we move on to next. So we look at an example. And then now here's the key part that, new part that we are moving, today's new part. So once we have this notion of reservant in the first order logic reservant, I will just call it first order reservant, then we can define the proof system for first order logic. So the proof system is talking about the derivation, just like the propositional resolution proof system talk about derivation. The definition is exactly the same. Derivation of C from a sequence of clauses C1 up to Cm. It is nothing but, the derivation of C is just a sequence of clauses C1 up to Cm, such that the last guy in the sequence should be the same as what we are deriving, so C. And then each guy is either coming from an assumption, or it should be derived from two previous clauses using this resolution proof rule. In other words, Ci should be a reservant, first order reservant from the two previous clauses in the sequence. So the first case says Ci is a clause from F with possibly variable renaming, or it's a reservance of Cj and Ck from where Cj and Ck should appear before Ci. And then we write the notation res star F to mean the set of all the clauses derivable from F. So here's an example that I wanted to solve, okay? So I will just give you, no, not this one. Okay, so here's a big example I wanted to solve. So suppose that we want to prove F1 conjoined with F2 implies F3 in this case. The semantically implies F3. So that's what this notation is telling us. And then that means if we prove this by contradictions, we want to show F1 and F2, and the negation of the conclusion leads to the contradiction. In other words, F1 and F2 and negation of F3 is unsatisfiable. Now, use what we learned so far, which is we learn about colonizations and first order logic resolution. Use all of these to derive the contradictions in this case. In other words, derive first to the colonization of the formula F1, F2, and negation of F3, and then do the resolution, derivation in the resolution, which is gonna be a sequence of clauses. So there will be a sequence of clauses C1 up to Cm, such that because we want to prove this contradiction, so we want that the last guy is a box. In other words, it's an empty set. Okay, so I will give you 5 minutes to solve this problem. But before actually I'm asking you to do this, Let me tell you what this actually formula means. This formula really coming from, so A is an axiomatization of addition. So it doesn't have to be, but I mean, this is the example of the axiomatization of addition in, I think, piano arithmetic, or maybe, yeah, piano or Pressburg arithmetic. But anyhow, so A describe an addition. So intuitively, what it says is A x, y, z means, intuitively means that z is x plus y. And S means a successor. So in other words, it means plus one operation. E means zero. Okay. So what does this means? This means that 0 plus x is equal to x. So that's how we axiomatize addition. I mean, one of the first axioms for addition. The second one, if you view this as an implication form, is say A x, y, z implies A of x, x, y, s of z. In other words, if z is equal to x plus y, so then s of z, so which means z plus 1 is equal to s of x plus y. I mean, this is what you typically expect. The last guy said, for every x, there exists y such that, I mean, this represents number 2. Say 2 plus x is equal to y. I mean, because there are infinitely many natural numbers, I mean, this is going to be also going to be true. Okay, anyhow, so that's a axiomatization of addition, but I mean, you don't really need to understand this intended meaning for this exercise to supply colonization and further the logic resolution to prove, I mean, the F1 and F2 and negation of F3 is unsatisfied. So I'll give you 5 minutes to do this. Okay, so the next slide actually have a solution, but I think it's better for me to just show you how it works. Okay, use this one, keep it. Okay, right. So for this exercise, we want to derive a contradiction. So we have F1 and F2 and negation of F3. Now F1 and F2 are already in Scholen form. We're going to apply the parallel Scholemization. Okay, they are already in Scholen form. So we only need to Scholemize negation of F3. But for negation of F3, we use a De Morgan's law that's equivalent to this X for Y, negation of A as applied twice to E and X comma Y. Now we said for Scholemizations, although we often talk about functions, if we just have an existential quantification, we can introduce a new constant symbol. So in this case, we're gonna introduce new constant symbol C, Scholemizations, and it's gonna introduce constant symbol C. So the Scholemized formula, which we will write G3, is gonna be written as for Y, negation of A, and SS of E in C and Y. So what we have to do is we have to apply the resolution proof step to F1, F2, and G3 to derive a contradiction. Okay, so how should we do it? So the proof in the resolutions is just nothing but a sequence of clauses. So the first clause that we're gonna obtain is from G3. Okay, so we will take first clause, which is a singleton set, that is A, SSE, and then we will rename all the variables whenever we so that the variable in clauses are always unique. Okay, so we're gonna rename Y to Y1, fresh variable Y1 here. Now, for the seconds, we will now use F2. So the plan is G3 is what we want to use. And in some sense, F2 talk about, in a sense, inductive step. F1 is talk about base step. So that our overall proof scheme is, because we want to talk about adding 2, we will have to, if you want to go all the way back to the very basic definition, when you add number 2, you have to recurse twice. So once for reducing 2 to 1, another to reduce number 1 to 0. And then when you hit the 0 case, we can use the base case. So what's going to happen in this, even in this proof setting, is that we will apply this F2 twice. We apply the resolutions with F2 twice. And then we will get something. And while we get something, if we apply the resolution with F1, we'll be able to derive a contradiction. So very much like the computation of adding number 2 to some number. So how should we do it? So we instantiate F2. So here's a clause that's coming from F2. So we rename all the variables C2, and then A of S of X2, Y2, S of Z2. Now the third clause is going to be obtained by applying the resolution to clause 1 and clause 2. So to apply the resolutions, we have to do cancellation. So our plan for doing cancellation is we want to cancel this guy and this guy. But to do this, we need to first call the unification. If we call the unification for this clause and then the corresponding clause in the second, and corresponding literal in the second, so the literal from the first clause and the corresponding literal in the second clause. And if you call the unification between, I mean, for those two, that when negated version of the literal from the second clause, then what we get, substitution we get is, we say that we have to replace x2 by s of e, and then the substitution said we have to replace y2 by c. Also, we said we have to replace y1 by s of z2. So that's what we get using when you call the unification. So we have s of e is going to replace x2, and then c will replace y2, and then the s of z2 will replace y1. So this is what we get when we call the unification. Now, after this guy, we want to apply one more variable renaming, so that all the variable that appears in the step 3 will be different from any other variable appearing so far. So if we apply this substitution, the variable that survive, because I mean, there are variable x2, y2, z2 in the remaining literal. The only variable that survive is z2, and we want to rename z2 to something fresh. So we will, instead of s of z2, we will rename this to s of some fresh variable z3, and we will also apply substitutions that will rename z2 to z3. So in the slide, I'm using this substitution one after the other. This is more like a simultaneous substitution. x1 get replaced by s of e, y2 get replaced by c, y1 get replaced by s of z3, and so on. So if we apply this substitution, these two guys will cancel in this case. And then the remaining one will be coming from this negation of a, x2, y2, z2. So we have a x2 get replaced by s of e, y2 get replaced by c, z2 will be replaced by z3. Okay, now we maybe just erase this because I want to apply. Okay, so now we apply the induction, in a sense, the rule F2 once. So we're gonna apply resolution proof step on using F2. So this time we're gonna apply the resolution to these two guys. So in this case, the resolution will be applied to cancel this one and this one. And when you apply the resolutions, the corresponding substitution is now going to be x2 will be replaced by e. Then the y2 will be replaced by c. And g3 will be replaced by s of z2. But just like before, we want to use some fresh variables every time. So instead of g2, we're gonna use a new fresh variable z4, and z2 will be replaced by z4. Okay, so if we do this, then only this term will survive, and the remaining one that we get is negation of a. x2 now becomes e, y2 now becomes c, z2 now becomes z4. Okay, so we, in a sense, apply the induction twice. And now, well, we want to one more time, apply the resolution one more time. But this time we're gonna apply the computer reservance between what we have, which is clause in number 4, and the clause that's coming from the first formula F1. So we instantiate the first formula F1, which is going to be A, E, X5, and X5. Now if you, this time, we're gonna apply the resolution such that these two, green underlined literals will be canceled. So if we call the unification by putting the negation here, so then the unification will return and said X5 have to be replaced by C, and Z4 have to be replaced by C. Okay, so X5 will have to be replaced by C. So then X5 becomes C here. Z4 now have to be replaced by C. So if we do so, then compute the reservance. In this case, that's going to be an empty set because these two green underlined literals will be canceled. Okay, so that's what we get here. And this means this is the same as box. So this means that we derive the contradiction by using this resolution proof system. Okay, I hope you have some idea about how all this works. So you can see this whole entire, throughout this process, we are not really applying the substitution before. We are always applying the substitution on demand, only when we have some clear idea which terms should be canceled with each other, which terms should be canceled with each other, okay? So the substitution that we are applying here is, in a sense, on demand. Okay, so now on to the next. So then now the natural question next that pops up is why this whole thing is okay. And this whole thing is okay because of the resolution lemma, just like the resolution lemma in the first order logic. And this resolution lemma say, if we have a formula F that is a closed formula in Scholen form, and then G is a quantifier free and CNF, and R is a reservant of two clauses in G. So then adding extra reservant, conjoining this extra reservant to G doesn't change the meaning at all. So that's what this thing is saying. So here, the union should be really understood as a conjunction, because now I'm viewing this conjunctive normal form formula G as a set of sets. So really this union outside really means that the conjunction. So this really means a bunch of universal quantification like x2 and for xn and G conjoined with extra reservant R that we obtained here. And then the star notation is just say that, for any variable appearing in G conjunctions R, we're gonna quantify all those variables universally. So that's what this for all star means. Okay, so that's what this resolution lemma says. Intuitively, the lemma says that what we obtain by applying the resolution proof step is redundant. It doesn't add anything. Okay, so that's what this lemma is telling us. Okay, so here's an exercise I want you to think about, and I'll give you 2 minutes, well, 3 minutes to do so. The first exercise is, suppose we want to prove this resolution lemma. Then one direction is obvious and the other direction is not. So think about which direction is obvious. The second, for non-obvious direction, think about how we can prove this lemma. Okay, I'll give you 3 minutes to do so. Okay, so show this again. I mean, for this, the proof of this lemma is actually quite easy. So I mean, what we have to prove that I will think about some very simple case where f is, say there is only one universal quantification. Many doesn't really matter. Proof is exactly almost gonna be exactly the same. And then we for this for universally quantify the star of G union R. Say this is again, there is only one universal quantification for X, G, and R. Set. Okay. So this is the case, and what we have to prove. What we have to prove is have to show F in Korean. So we have to prove two things. The first thing we have to prove is what we obtained for X, G, and R. That implies for X and G. That's one thing we have to prove. Another thing we have to prove is this guy for X, G semantically implies for X, G, and R. And these are the two things we have to prove. Proving the first is quite easy. I mean, there's this in terms of definition, which means that for any structure A, if A satisfies for X, G, and R, that implies for any structure A implies for X and G. So structures A. So this is what we have to show. But then showing this is obvious. That's because if you just unpack the definition of this guy, and that will, from that definition, you can just see that A, well, we just do this because it's a really easy directions, but the above definition say for A, assumption set is gonna satisfy G and R for any A in the underlying universe of A. Now, if the updated structure A satisfies G and R, that means of the structure A satisfies G for any A in U of A. So we can conclude that A satisfies for XG. Okay, so this part is reasonably easy. And a bit more difficult part is for this direction. Okay. And it turns out showing this direction is the same as showing this for X, G plus R. So showing, so 4 is just bound here. And then X, if it appears in R, that's going to be a free variable this time. Showing that if we can show that below, we can easily prove the implication on the top. And I mean, that's because if you just follow the definition of A, I mean, this you can see that the one below implies the one above. I mean, it's not very difficult to show this. Okay. So then the focus has to be how we can show this guy. And now, because R is a reservant in first order logic, there has to be two clauses, C1 and C2 clauses in G. Then there also have to be most general substitution. And then also there has to be some subset D1 of C1, D2 of C2, such that if you apply the substitution D1 theta, and that's gonna become same as D2 theta with the complement. Okay, so because these two things will be cancelled with each other, so that's what happens. And another thing we know is this R is obtained by applying the substitution. And let's call this as an L. And then removing L from R and union for C2, apply substitution and remove L bar. That's a usual definition of the resolution. So that's what we know because R is obtained by the resolution. So we have to prove this if for x dot g is true under some structure, that structure also satisfies R. So we assume pick a structure A that satisfies for x dot g. Okay. And then because G inside contains C1 and C2. So G looks like C1, C2, and a bunch of other stuff. G contains C1 and C2. And also it contains universal quantification. Right? Because there is only one variable x, this substitution will have the form x gets mapped to some term t. And now, because of this, what we know is that by the definition of this satisfaction relations for the universal quantification, we know for x, in this structure, if you change the binding of x by its meaning of term t, that will satisfy C1. Also, we know that Ax is a meaning term t will satisfy C2. Now, by the translation lemma, that we talked about before, which say how semantic substitution and syntactic substitutions are related. The first guy here, this implies A satisfies C1, where X is replaced by T. And this second implies A satisfies C2, where X is replaced by T. So far what we do, we just look at the definition of, the first order resolvents, and then figure out there exists some bunch of stuff like C1, C2, and substitution. And then we just use our assumptions which say that A satisfied for x dot g. So now, this is same as C1 applied to substitution, same as C2 applied to substitution. Now C1 is gonna contain L because C1 with a applied substitution theta will contain D1 theta, which will be a singleton set L, so it will contain L. C2 with this substitution will contain L bar. Okay, because L and L bar are complementary, we have either A satisfies L or A satisfies L bar. Okay, and then each of the case, if we do case analysis, we can show now that A satisfies this resolvent R. So this is what we have to prove, and you can prove this by case analysis. So I will do the case analysis only for the first guy. In the first case, if A satisfies L, which means that, and then we also know A satisfies C2 theta, okay? So if A satisfies L and A satisfies C2 theta, but C2 theta contains L bar, A1 satisfies this guy, and then satisfies something other than L bar, because this set represents a disjunction. So which means that, maybe just use a red line. So in this case, by combining these two, can say A have to satisfy C2 theta minus L bar. So A have to satisfy, but this entire set of literature is included in R. R contains more cases. And then the set R represents disjunction, so A also, this implies A satisfies R. And then the other case can be proved very, essentially the same way. So that's the proof for the in the simplified setting. But the idea is, it's not very difficult. It's just that we look at these definitions. We just figure out what we have to prove, and then they simplify it and focus on the case that we really, this for xg implies r, so that's the case we have to focus on. And then we just look at the definition of first order reservants. They will give us C1, C2, and this is theta. And then we pick the structure which satisfy our assumption. And our goal in this case have to show the one I shown below. But if we just put all the puzzles together, all the properties of every data that we have so far, then we can derive the contradiction quite easily. And then essentially there's some big step in the proof. Maybe, yeah, like the ones that's going on in this argument here. That's, this is essentially the same as the proof of resolution lemma for propositional logic. So, which is really based on the case analysis. Sorry. Yeah, so proposition which is really based on the case analysis. Okay, so that's how this theorem is proved. So then, so here's a proof about this. And using resolution lemma, we can show that the first order resolutions, that is actually a sound way of proving contradictions in the, sound way of proving contradictions for first order logic. So it says that if F is a closed form formula in score-length form and G is quantifier free and CNF, if there is a derivation of a box, which is a contradiction from G, then F should be unsatisfiable. And although I said it's an exercise, it's actually quite easy. The proof is say that if we have a resolution derivations of a box, that means there is a sequence of clauses C1, C2, Cm, such that the last one is equal to box. But what this resolution lemma tells us is that every clause in this sequence, when we combine all of them with F, then that's going to be equivalent to the original formula. So which means F is equivalent to, for all, start here, well, start up, forgot, and G together with C1, C2, and Cm. But Cm is a box, which means which is the same as false. So if something is equivalent to false, so that means F should be unsatisfiable. That's how you can prove the soundness of this resolution proof system for first order logic. Okay, so that's the whole entire reasoning is exactly the same as before. Now let's move. So this shows that what we are doing is okay. If we derive contradictions, so then that really means a contradiction. But now the next question, the other question is, now can we derive all the contradictions by using this rule? And it turns out that is the case. So that's what this completeness theorem, next completeness theorem is telling us. So if we have a closed formula in score-length form, G is quantifier free and CNF. Now, if it's F, we said if there is a resolution derivation of a box from G, F should be unsatisfiable. So this means our proof system doesn't lie to us. Now, this completeness theorem say our proof system is actually very powerful. So it can detect, it allows us to prove all the unsatisfiable cases. Okay, that's what the completeness say. If F is unsatisfiable, there always exists a resolution derivation. There always exists a proof in this new resolution-based proof system. So this type of result tells us actually our algorithms never misses anything. If we design an algorithm or semi-algorithm based on the result, this first order resolution that we discussed so far. So now the question becomes how we can prove this. So, actually proving this is not entirely obvious. So I will give you a hint, which is called the lifting lemma. And maybe I will give you 5 minutes to think about this. Then I will tell you how you can prove completeness using this lift lemma. So try to prove this completeness using lifting lemma. And so I think one more things you have to use lifting lemma, and I think it's called resolution theorem. I forgot exactly the exact name, resolution theorem, in the previous lecture. Which say using the first do the grounding and apply the resolution, you can derive all the contradictions. So that's what our resolution theorem tells us in the previous slide, in the previous lecture, and then try to use this lifting lemma and resolution theorem to prove this completeness. And if you manage to do this like less than 5 minutes, then you can also think about the next question, which is how to prove this lifting lemma. Okay, so let me show you how to do this. Okay, just make a bit of this. Right. Hmm. Okay, so let's try to prove the completeness. So I will just show I'm not going to give you really detailed proof, but I will give you one like pictorial description about how proof works, a key idea of the proof. And by the previous lecture that I've talked about, so start with F. So let's say F is unsatisfiable. So suppose that F is unsatisfiable. And we want to show there is a resolution derivation, first order resolution derivation in this first order resolution proof system of box from the, from the matrix of G, for matrix of F, which is, so F has this form for X1, 2, for Xn and G. Now, by the resolution theorem that we studied before, something that we know is that if it's unsatisfiable, then there is a ground resolution proof, which means that there are, so this is G. Okay, let's just expand all the component here. Well, let's just write it here. So G is really some cloud C1, C2, up to some Cm. So there is the ground resolution proof, which means that there is a grounding of some C1 with some groundings θ1, apply substitution. Not necessarily C1, maybe some Ci1. And then maybe, so this is a specific substitution, so it replaces variable to ground terms. And then maybe Ci2 with substitution θi2. So this is a ground substitution again. And then they get, apply the resolution proof step, which does the cancellation a little bit. That will reproduce some C prime. And then maybe there's another Ci3 that's coming from this ground instance. And then they may get resolved in C double prime and so on. So, and there are another branch, possibly Ci4, θi4, and Ci5, θi5 get resolved and theta triple prime, and these maybe get resolved and lead to a contradiction. So there is a proof, in the ground resolution proof system. Okay, so everything, all the clauses from F, whenever we use it, they are grounded completely in the sense that all the variables will be replaced by ground terms without any free variables. And then we just apply the ground resolution as if things are in the propositional logic. So, and then the theorem that we studied before, which is the ground resolution theorem, tells us if F is unsatisfiable, there is such a proof in the ground resolution proof system. So this exists because of grounds resolution theorem. Okay. So now what should we do? But what we are not looking for this type of a ground, the proof in the ground, derivation in the ground proof resolution system. We are interested in having derivation in first order resolution proof system. Okay, so this is not good for us. Not good for us yet. because it's a ground proof system. So what we are doing is we're gonna use this lifting lemma to lift this proof in the ground resolution proof system into proof in the first order resolution proof system. And then the lifting lemma said, look at, so let's think about how to do this lifting. To do this lifting, the natural way of doing lifting so we're gonna lift everything here so that all these things, this tree, after the lifting, will form the proof in the first order resolution proof system. So the way to lift these leaves, okay, is just to use a CI1. I mean, I'm not going to express renaming, but we just reuse CI2, CI4, CI5, CI3. Okay? Because that's okay, that's because in the first order logic resolution, we can use a clause which can contain variables. Here, all the clauses after substitution, none of them contain variable. Here we contain variable. And that's actually the key idea of first order resolution proof system. Now the difficult part is now we want to lift these intermediate guys, like this one and these guys, such a way that we have a reservant corresponding first order reservants from CI1 and CI2 and so on. So how should we do it? And that's the place where we can use this lifting lemma. This lifting lemma said, if we have something like CI theta 1, which is a ground instantiation of the clause CI1, CI2 theta 2, which is another grounding of CI2. And then if we perform the computed reservant using these grounded instances, and there is actually a first order instance, a first order reservant called R prime, such that this C prime is on grounding of R prime. Okay, so some relationship that's true is that satisfy the grounding relationship. These two guys also satisfy the grounding relationship. But the lemma said if we compute the reservant to C prime using the grounded clauses, then there is a first order reservant R prime, such a way that these two guys are also in this grounding relationship. And in a sense, this grounding relationship is the only things that's needed to lift this resolution proof step in the grounded case into the resolution proof step in the first order case. So we do the same thing. This C prime and R prime are in grounding relationship. And then this, maybe use green. These two guys are in grounding relationship. And this CI3, theta I3, and then just CI3, they are also in the grounding relationship. Now, this means that this C double prime, which is obtained from C prime and two grounded instances, then there exists corresponding first order reservant R double prime, such that C double prime and R double prime are also in the grounding relationship. In other words, if we apply substitutions in R double prime, we can obtain C double prime, and so on. So if you keep doing this by the same reason, we can construct R triple prime. And now R triple prime and C triple prime, they will also satisfy the same kind of relationship. So then just like we have a box in the derivation, there is some R4 prime, which is a first order reservant of R triple prime and R double prime, such that in this guy, the box, and then our triple prime are in the ground relationship again. But the only way because the box represents the empty set, the only way this grounding relationship true is our triple prime, 4 prime is equal to the empty set, which is itself a contradiction. Okay, so that's how you can prove the completeness theorem. Whenever from the previous ground resolution theorem, there is a derivation of a box among the grounded clauses using the resolution proof step. Now, each of the proof steps can be lifted to the first order case because of the lifting lemma, and then because each step can be lifted, and the only way to lift box is box, then we can construct a contradiction here. So this proof that we obtain is this guy. So that's what you see at the bottom, that's the proof we can obtain here. So it's a bit like doing some kind of simulation on the level of a proof. So we have a proof in one proof system, and then this lifting lemma say actually each step of the proof in one proof system can be lifted, have a corresponding proof in a different proof system. Okay, so for the lifting lemma itself, I'm not going to go to the proof about lifting lemma. If you are interested, you can have a look at the lecture note, which contains a proof about it. Okay, so that's it for this part on the first order, the resolution. Does anybody have any questions about this? Okay, so then we'll move on to the next part, which is the compactness of a first order logic. And as I said before, some people say compactness is one of the most important results in logic, and especially people working on so-called model theory, compactness is a really important part. This is from one of the bases. And we discussed about compactness for propositional logic, but here we're gonna, and also I think we discussed something related to compactness when you do the proof of the resolution theorem in lecture 11. But here we're gonna directly prove the compactness for first order logic and use it to derive some interesting consequences about first order logic. Okay. So the compactness theorem say the following. So suppose S is a countably infinite set of first order sentences. So sentence means that formula without free variables. And then this compactness theorem said, if this countably infinite set S is satisfiable if and only if every finite subset of S is satisfiable. Okay, so that's what this compactness theorem is telling us. So it's very similar to the compactness theorem in propositional logic. The propositional logic case, S was the countably infinite set of propositional logic formula. And we have a very essentially of the same kind of claim, which is the countably infinite set is satisfiable if and only if every finite subset is satisfiable. And as you remember, perhaps the way often we use this compactness theorem is take a contrapositive of this statement, which say that if S is unsatisfiable, if and only if some finite subset of S is unsatisfiable, and that kind of contrapositive statement has been used to derive an algorithm. Okay, now the one easy direction of the proof is that to show, the only if direction. In other words, this direction is really easy. That's because if the S is satisfiable, so that means there is a structure A. So this part means that S for some A, there is a structure such that A satisfies S means A satisfies every formula in S. So there's a structure that satisfies every formula in S. Then of course any finite subset is also going to be satisfied. They will all be satisfied by this structure A here. So that part is easy. Difficult part is the other direction. So that's the difficult part. So maybe in the remaining 5 minutes, one thing I want you to do is try to show this difficult part. And I will give you some hint. Okay, so the difficult, or maybe I will just give you big sketch about how the proof works. Okay, so the proof works like this, and just like you can see on the screen. And I'm gonna explain what all this means in the next lecture. But for this lecture, I want you to have a look at what's really going on here. So why this is an argument. And then one thing I want you to do is to pinpoint for each of the steps what kind of theorems that you learn is used there. So for instance, if you go in step number 1, go from the line 1 to line 2, maybe use some of the theorem that we learned before. Going from line 2 to 3, we use some other theorems that we learned before and so on. Some step, maybe just an obvious step, but identify which theorems looks like is used in it whenever we go from one line to the next line. Okay. So I will give you 3 minutes to think about this, and then I will kind of give you an answer, and then we finish and we go back to this slide on Wednesday. Okay, so let me tell you the answer here. So actually, so the proof goes like this. So we have this set S, which is a set of the first order logic formulas, and then we assume all finite subsets are satisfiable. So then we scholemize all of them. It turns out, it's a bit tricky. One has to be a bit more careful, but there is a way to scholemize all the finite subsets, everything in S into some formulas, in Scholem formulas. So you scholemize. Then by the parallel scholemization theorem, so this is first step implies the second step, because any conjunction of some formula and their scholemizations are equisatisfiable. So this going from 1 to the 2, that's going to be okay. Now going from this 2 to 3 means that every finite subset of Scholem formula are satisfiable. Then we have to say that their Herbrand expansions are satisfiable. And that's true because of Herbrand theorem. Herbrand theorem said if some formula, Scholem formula is satisfiable, then there is a Herbrand model. So there is a Herbrand structure that satisfies the formula. And then actually the Herbrand, so the Herbrand model is essentially identical to this Herbrand expansions. That something is true on the Herbrand model, saying the same thing as this Herbrand extension is satisfiable. So in the propositional logic sense, so the going from step 2 to step 3, it tells us you can just use a Herbrand theorem. And now if for going from step 3 to 4, now we can use the theorem, the compactness theorem for propositional logic. Because once everything is a Hurban, if we only have this Hurban expansions, there are no variable at all. There are only ground terms and ground literals in first order logic. Then in that case, things can be regarded as a propositional logic formula. So we can apply the compactness theorem for propositional logic. So that going from 3 to 4 is the compactness of the propositional logic. From 4 to 5, this is just by definition. So if you just look at the Hurban expansions, if that's a satisfiable, that implies T has a Hurban model. So this is by definition of Hurban T expansion. And finally, this going from 5 to 6, that is again corresponding to parallel colonization. Because colonization is preserved satisfiability, so that's why we can go from 5 to 6. Okay, so that's it for today. Before finishing, let me just mention one more thing, which is right now we are talking about compactness theorem for countably infinite set. It turns out, I think compactness theorem also holds for uncountable sets, and that kind of thing is used often in model theory. And some theorem that we're going to talk about at the end, which is called Upward-Loeheim-Skolem theorem. That's the proof of this is using the compactness for uncountable set. Okay, so that's it for today, and see you on Wednesday.